right, so before the break, you guys were working on filling in all of the angles and all of the coordinates of the points for the unit circle. And we said you could use the 30, 60, 90 right triangles. If you remember those patterns, you could use the Pythagorean Theorem. You could use right triangle trig. Just to kind of refresh our memories as to how that worked. For example, if I took, let's say, the 60-degree angle right here, okay, this is a unit circle, so I knew that the hypotenuse was 1. And if you used your calculator, you were able to figure out that, if you used SOHCAHTOA, sine, cosine, or tangent, we needed to figure out the x and y coordinates. So you could figure out the x coordinate by using which trig function of 60? Okay,
Sine.
so cosine. Okay, so cosine of 60 degrees would equal adjacent x over the hypotenuse 1. Okay? Now, obviously, x over 1 is just x, and then you type in cosine of 60 degrees into your calculator, and you get 1/2. Okay? Then, I told you, if you use sine to find y, you would have gotten like a 0.866. Okay? But I had told you to make sure that you find everything in terms of the radicals. So rather than using sine and coming up with a decimal like that, at this point you could use the Pythagorean Theorem with the 1/2, the 1 for the hypotenuse, and then the y. So 1/2 squared plus y squared equals 1 squared, which is 1. So 1/4. We'd subtract from both sides, so we get 3/4 is y squared. And that means y is the square root of 3/4. And you notice square root of fraction, you can just take the square root of the top over the square root of the bottom. And that is how we get root 3 over 2. And that's how all of these coordinates can be derived. Okay? Doing it like this, and then also considering which quadrant we're in to determine whether they're positive or negative coordinates. Okay? So that's one of the things that you did the Friday before break. The other thing was simply converting all of these angles into radians. Okay? Now, our end goal here is that you will know this so well that I'll be able to say, what is the sine of 240 degrees?
-1/2.
Okay, and you'll be able to think through, and you'll remember what we actually identified was that the x coordinate ended up being the cosine. Okay. And the y-coordinate ended up being the sine. And that's why we learned these coordinates, is because now, if we know all of this, we know the sines and cosines of all of these angles. And these are very commonly used angles. Okay? So, let's start looking at some of the patterns in this. Hopefully, I think a lot of you recognized a lot of these patterns. One thing I will say is, as we're doing this, make sure that your unit circle that you filled out is 100% accurate. Okay? Because if you have a mistake and then you're memorizing the wrong thing, that would be tragic. Okay? So we want to make sure that we have everything 100% accurate. Okay? Now, I gave you the angles, and I showed you on the angles with degrees the patterns. if you recall, the way we came up with all these angles is, first of all, we took these quadrants, 0 degrees, 90 degrees, 180, 270, and then back to 360. And first of all, we divided them into 30s, okay? So we have 30, 60, 90, 120, 150, okay? 180, 210, 240, 270, 300, 330, and 360, okay? So that's the first pattern. It's just how we got those angles. Now watch here with our radian degrees. This is a part that I didn't give you, but I bet you picked up on somewhat. Okay? 30 degrees is pi over 6. Okay? So instead of counting up by 30s, now we can count up by
Pi over 6.
Pi over 6. So the difference here, though, and this is why people sometimes don't recognize this pattern, okay, is that we reduce the fractions as we count up by 6, pi over 6.
Pi 6 plus pi 6. Pi over 6 plus pi over 6 is like 2 pi over 6, but you really just pi over 3.
Yeah, 2 pi over 6. What's 2/6? It's 1/3, so that's pi over 3. Then we count up another pi over 6, so 3 pi over 6. Well, 3 over 6 is a half, so this is pi over 2. Okay? 4 pi over 6. 4/6 is 2/3, so it's 2 pi over 3. Then we have 5 pi over 6. Then we have 6 pi over 6. 6 over 6 is 1, so that's just pi. Then we have 7 pi over 6. 8 pi over 6 can reduce to 4 pi over 3. 9 pi over 6. 9 over 6 is 3/2, so it's 3 pi over 2. 10 pi over 6. Okay, 10 over 6 is 5/3. And then 11 pi over 6. And then 12 pi over 6 is 2 pi. Okay, so you see here we're counting up by pi over 6 every time.
That's fun.
Okay, seeing that pattern will help you. Okay?
And you want us to take these notes on the actual units, right?
You don't need to write down the patterns. Like,
Oh.
I'm not going to ask you to list the patterns, but seeing the patterns will just help you as you memorize and stuff. Okay? Now, what are some patterns that you recognize just in that? Do you see anything with the radian degree or the radian measures of the angles?
When you go around once, you get 1. And when you go around twice, you get 2. Like, so whatever is across, like it's always 1 more.
Oh, like from pi over 6, if you go straight across, you're at 7 pi over 6, that's plus a pi. Okay. What else do you notice about the ones across from each other? Like pi over 6, 7 pi over 6, pi over 3, 4 pi over 3, pi over... They have the same denominators, okay? And actually, this relates back to what we call reference angles, okay? Reference angles, and we'll touch on this more later, but a reference angle is an angle, if you pick a point on the unit circle, it's the angle that we form with the x-axis, okay? So these two angles, pi over 6 and 5 pi over 6, have the same reference angle, okay? 11 pi over 6, okay? And 7 pi over 6 also have the same reference angle as the other two. Now, a reference angle is always going to be between 0 and 2 pi, or between 0 and 90 degrees. Okay? So this first quadrant angle is the reference angle, but these four angles, pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, all have the same reference angle, pi over 6. Okay? This is one area where radians are actually easier to work with than degrees are. Because if you see the same denominator, you know they have the same reference angle. Okay? So that's another pattern that you can see here in the unit circle. You can see the reference angles with our radian measures for our angles. Okay? Pi over 3 has the same reference angle as what other angles?
2 pi over 3.
Good. 2 pi over 3, 4 pi over 3,
5 pi over 3.
and 5 pi over 3. Good. Okay? So you can see those reference angles. Those are another pattern.
And that's basically the denominators, right?
Yeah, if you look at the denominators, when you're looking at the radian measures, the denominator will tell you if it's the same reference angle or not. Okay, of course we're talking about reduced fractions, but so if I had pi over 5 and I had 4 pi over 5,
Is the reference angles?
even though those aren't on the unit circle, they both have the same, they still have the same reference angle. And 6 pi over 5 and let's see, 6 pi over 5 and 7 pi over 5 would as well. Okay. Alright, so those are all some different patterns within the radian measures. Okay, I want to look now at the coordinates of the points. Okay, the coordinates of the points. You guys picked up pretty fast on the fact that these triangles are all going to be 30, 60, 90s or 45, 45, 90s. Okay, and as you started to figure out what the sides were, you recognized, hey, I have the same triangle here as I do over here. It's just I'm moving over to the over here to the second quadrant, so I know my x coordinate is negative. Okay, and this is why all of these points have the same coordinates. It's just the signs are different. So here's another pattern that you'll want to notice. Okay, in our first quadrant, all of our coordinates are positive. Okay, over here in the second quadrant, our x coordinate is negative, but our y coordinate's positive. Here in the third quadrant, both coordinates are negative. And in the fourth quadrant, the x is positive, but the y coordinate is negative. Now, why is that significant? I mean, that's something that you learned back when you first started graphing points back in, I don't know, 5th or 6th grade.
Because you only have to memorize the first set of like coordinates, and then you could just use like the reflections.
Exactly. If you memorize this first quadrant, you've got the whole unit circle, basically. Okay? And really, that's what I want you to get in here, is not, I mean, you'll get to the point where you can just pick out, hey, 7 pi over 6, that's 210 degrees, that's a negative root 3 over 2, negative 1/2. Okay? You'll be able to pick that out eventually, but especially as you're learning it, see those patterns and see how it works, okay? Because then you'll start to see, hey, any of the pi over 6s are going to have a root 3 over 2 and a 1/2. I just got to figure out what the signs are. Okay? Which quadrant am I in? Now, another reason why that's significant is because what is the x coordinate on the unit circle?
Radius, so like the one.
Now, the radius isn't the x coordinate. The radius is our hypotenuse.
cosine of the degree.
It's the cosine of the angle. Okay? So what do you notice about any angle that's between 0 and pi over 2? Its cosine will be positive. Okay? Alright? What do you notice about the cosine of any angle between pi over 2 and pi? It's a negative. Okay? Any angle between pi and 3 pi over 2 is going to have a negative cosine. And any angle between any angle between 3 pi over 2 and 2 pi is positive. Okay? Alright, so you'll see here, cosine is positive in the first and the fourth quadrants, but it's negative in the second and third quadrants. Now we're going to learn a real easy pattern to help us remember what's positive where. Okay? But let's keep going with this. Okay? What is the y-coordinate on all of these points? It's our sine. Okay? So in the first quadrant, our sine is positive. In the second quadrant, our sine is positive. In the third quadrant, our sine is
Negative.
and in the fourth quadrant, our sine is yeah. Okay? Our sine is negative. Now, there's one other trig function that we don't see directly, but we did mention how we could get it. Okay? What's our third trig function?
Tangent.
Tangent. Okay. Tangent, if we look back here, if this is our angle, the tangent of theta would equal what?
Y over 1/2.
Yeah, y over 1/2, and that would equal 2y. That's good. Okay? And the key thing I want you to recognize here is that 1/2 was our x coordinate, right?
So Y over X.
So it's y over x. Now, what's the y coordinate?
Cosine.
No? The y coordinate
Sine.
is sine. And the x coordinate is cosine. Okay? This is one of the identities that we're going to use a lot. And that is that the tangent of any angle is sine over cosine. So not only does our unit circle give us the sine and cosine, it also allows us really quickly to figure out what the tangent is. Okay? Now, let's think about the signs of these. If I'm dividing sine by cosine, tangent is going to be positive in the first quadrant. What will tangent end up being in the second quadrant?
Negative.
Negative, because a positive divided by negative is negative. Alright, how about the third quadrant? It's positive. Two negatives will make a positive. And in the fourth quadrant? Negative. Yes. Okay? So, here's what we have. Okay? Let's notice here what is positive in each quadrant. Okay? How many of the trig functions are positive in the first quadrant?
3.
All three of them. All of them. Okay? You don't need to write it over the entire thing, but okay, all of them. What's positive in the second quadrant? Sine. Okay, sine. In the third quadrant,
T.
tangent.
Are you gonna spell something?
Sat.
Here's what I'm thinking.
See, those.
Cosine.
Sat.
Sect. Okay, now, here's the thing. The way I learned it,
Cats.
was as ACTS, ACTS. But that goes backwards in relation to how the quadrants are numbered, so some people find that confusing. What more people find helpful though is just to go in the same order that we are going as we rotate around the unit circle. And if you remember that all students take calculus,
Yeah.
it's really easy to remember, okay?
Or if you start from the bottom when it's cast.
Yeah, cast. So however it helps you remember, okay, the nice thing about all students take calculus is it goes quadrant 1, 2, 3, 4. Okay? So that's probably the easiest people have found to use, okay? So when you're thinking about, hey, what is the tangent of a 5 pi over 6? You're thinking, okay, 5 pi over 6 is less than pi, so I'm in the second quadrant. Tangent is only sine is positive in the second quadrant, so I know tangent has to be negative. Okay? And believe it or not, these are the kinds of mental gymnastics that you're going to be able to do really, really fast by the time we're done with this. Okay? So that's what we're working to, and that's why we gotta memorize this and really, really work hard to understand it. Okay? Now, we talked about one identity already, and we'll work a lot with these identities in the days to come. But another set of identities I want you guys to be familiar with, and this is where you may want to take some notes not on the unit circle, but another set of identities is what we call the reciprocal identities. The reciprocal identities. And this is where we actually get the other three key trig functions. Okay? These are the reciprocal functions, or you could call them the reciprocal identities. Okay? And you'll notice here, it's only one thing, okay? I just stated it both directions. The reciprocal of sine is cosecant, okay? Cosecant. The reciprocal of sine is cosecant, right? Now, these are reciprocals of each other, so sine is the reciprocal of cosecant as well, okay? It goes both ways. You can see there how to spell it, cosecant. Now, the reciprocal of cosine is secant. And finally, this is the easiest one to remember, the reciprocal of tangent is cotangent.
It's frustrating how like cosecant is not with cosine.
It is a little frustrating, but it makes sense later, okay? The easiest way to remember this is that there's only one co in each pair. Okay? So sine, cosecant. Cosine, secant. Tangent, cotangent. There's only one co in each pair.
Gotcha.
Okay? Now we're going to see on Thursday how what we call the cofunctions go together. Sine and cosine go together in a different way. Secant and cosecant go together in a different way. And then cotangent and tangent go together again in that same way. Okay? But for these, the reciprocal function, sine goes with cosecant, cosine goes with secant, and tangent goes with cotangent. Okay? So one of the things that we're going to do to practice, and after we look at this, I'm going to give you time to practice a few different things here, is if we're given any point, we can find the value of all 6 trig functions of the angle and standard position that passes through that point. Okay? Let's look at an example here. Let's get rid of that. Okay. And see how we would go about doing this. Alright? So, I took some from your book here, and we're going to start by, first of all, sketching the situation. Okay? And if we're given any one of these trig functions, then we can automatically tell what all the other ones are. Okay? All 6 trig functions. So we can actually even write out, okay, sine of theta equals cosine of theta equals tangent of theta equals cosecant theta, secant theta, and cotangent of theta. And just so I don't erase those, I'm going to just group those all together and lock them. Okay. Now, in this case here, we know that the cotangent equals 5. We'll do part 10 here. Okay? The cotangent is 5. So what does that mean? What else of these could we figure out?
Tangent.
Tangent. Tangent equals 1/5. Okay? Now, tangent is positive. That means we're either in the first or third quadrant, okay? And they're telling us to actually use a right triangle, so we actually know everything's going to be positive. Right? In this case, we know it's going to be positive. So I'm going to actually adjust this so that we're just in the first quadrant here. And you can see here that the tangent is 1/5. That tells us something about the right triangle that we're going to use. Tangent equals what over what?
Opposite over adjacent.
Opposite over adjacent. Okay?
1, adjacent 5.
Very good. So here I have this triangle. It would look something like this. Opposite must be 1 and the adjacent could be 5. Okay? Now, we know that in reality the opposite could be 2 and the adjacent could be 10 or something like that, as long as they have the ratio of 1 to 5. But it doesn't matter when it comes to trig functions because the angle will stay the same. Alright? So, with that being said, how could we figure out our sine and cosecant and our cosine and secant? What do you think?
Tangent equals sine over cosine.
Okay.
Can't you say that the sine over cosine equals 1/5?
We could.
No, well, I
Or
guess
can you use Pythagorean Theorem?
We-
How about this?
Okay. Sine over cosine would be 1/5. Does that mean sine equals 1 and cosine equals 5? No. And actually, we know for a fact that cannot be, because if you look at your unit circle, the biggest sine ever gets is 1. And the biggest cosine ever gets is 1. You cannot have a cosine equal to 5. So that's where using that's not a bad idea at all, but here we're going to get stuck at that point. And that's where using that Pythagorean theorem, what would our hypotenuse be?
1 squared plus 5 squared. So 1 plus, yeah.
Good, square root of 26. 1 squared plus 5 squared is 26. So square root of 26 is our hypotenuse. And guess what? Now we can use that SOHCAHTOA to get our sine and our cosine. What does sine equal?
1 over the square root of 26.
Good, 1 over root 26, which would equal, there you go, let's rationalize that, square root of 26 over 26. And our cosine would equal,
5 over square root of 26.
good, 5 over square root of 26, so that would be
5 root 26 over 26.
There we go. Okay? So now I've got my sine and cosine. And we can also now say that our cosecant equals
26 over radical 20. Oh, wait.
26
26 radical 20.
26.
No, it just radical 26.
there we go. And what you guys are all saying was right. If you reduced it completely,
Oh.
this is where going back to the part before you rationalized it is helpful.
Yeah.
It's square root of 26 over 1.
The next one, radical 26 over 5.
And the next one is square root of 26 over 5. Okay?
Here we are.
Okay? So there is our cosecant of theta is the square root of 26. And the secant of theta is square root of 26 over 5. Okay? Now, obviously, guys, if you have sine and cosine that always have to be a fraction less than 1, in fact, it always has to be between -1 and +1. When you take the reciprocal of a fraction, you always get something bigger than 1, right? So you know cosecant and secant will always end up being bigger than 1. All right? Now, tangent, cotangent are different. They, obviously they're still reciprocals, but tangent can be any real number. So you can have a tangent equal to 100 or something. So that one isn't like that. But sine and cosine always have to be between -1 and 1. And therefore, cosecant and secant will always be bigger than 1 or smaller than -1. Okay?
Do you think we turn this down as an example?
You could, sure. Let's try another one. Let's try, which one do you want to try?
17.
Well, we have 12, 14, or 16 right here.
14.
14, okay, let's try
Why would
14.
you choose 14?
Probably 14.
Well, actually, it's solving.
All right.
Because it's 7 times.
Okay, so here's 14. 14 says that my cosecant is 17/4. Okay?
Sine is 4 over 17.
Good. Sine is 4 over 17. And what is that, how can I draw my triangle then? What are those 4 and 17 going to be?
17 is the hypotenuse.
Good. 17 is
4
the hypotenuse.
Other side.
And 4 is the which side in relation to
Opposite.
theta? It's the opposite. So 4 over 17. Okay? Good. So now I can figure out this side here. 17 squared equals, make sure you set up your Pythagorean theorem right. Your hypotenuse should be the biggest side. Okay? 289 minus 16.
The square root is 273.
Square root of 273. Does that simplify? The radical simplify? It's divisible by 3. 91. And 91 is prime, I think.
It is.
So we're stuck there.
Fine.
Okay?
Use the restroom.
Alright. So, once you know all three sides, the rest of this is somewhat simple. Okay? So our cosine is what?
Root 273 over 17.
Good. Root 273 over 17. Okay? Our tangent would be
4 over radical 273.
good. 4 over root 273.
So 1092 over 273.
You're on the right track, but the 4 is not in a radical,
Right.
so it'd be
4 root 273.
Hitting the mix.
there. You go. Okay. Yeah, you can't multiply those because it's in the radical. But yeah, 4 root 273 over 273.
You gotta remember what's not.
Okay.
It would be 17 radical 273 over 273.
Okay, good. We flip our cosine, take the reciprocal of our cosine, and rationalize it. 17 root 273 over 273. And then our cotangent,
Radical continuity over 4.
there we go.
Very bones.
Okay? Alright, so for today, I want you to be able to see those patterns in the unit circle. I want you to be able to work with getting all 6 trig functions. Okay? Here, these ones are a little bit just slightly different. Okay? What you're going to need to do is use the coordinates to help you draw the picture. Okay? And what did we say?
Isn't hypotenuse 17?
It could be.
1.
In this case, it actually, yeah, in this case, you actually have coordinates, not a value of sine or cosine. Okay? So, in this case, actually, the hypotenuse ends up being 1 if you did the Pythagorean Theorem. Okay? It's not necessarily always going to come out to that, but in this case, it does.
Why is it 1 on the 17?
Well, if you do the Pythagorean Theorem with this, 64 over 289 plus 225 over 289 equals 289 over 289, so that's 1.
So the 8 goes in the bottom, right?
The negative 8/17. And one thing I will say, I know it doesn't make sense to have a triangle whose side is negative, but if you leave the negative from the coordinate in there, when you make the triangle, when you're doing the values of the 6 trig functions, okay, that'll help you make sure you get your signs correct, okay? Also, remember all students take calculus, so your sine and cosecant, therefore, should be positive. Your cosine and tangent should be negative, because we're in the second quadrant, okay? The other thing I will mention, this is something that you'll see in the directions a lot, okay? And they'll say either the exact angle or they'll say exact values of trig functions, okay? Whenever they're talking about exact, if they're talking about trig functions like this, they're saying leave it in radical form. Do not put it as a decimal, okay? If they're talking about angles, particularly in radian measures, they're saying leave it in terms of pi. Okay, don't give us a decimal for the radian measure. The angle, leave it in terms of pi. All right, so watch out for directions in these sections. Okay. All right. So I'm going to give you the remainder of the time to work together and ask questions. Okay. There's a few applications here near the bottom. One with harmonic motion, which is kind of a cool one. Harmonic motion is just when we have this thing oscillating back and forth, like a spring that's bouncing back and forth. Okay. This is called simple harmonic motion. But you can practice with some of these. This is exactly what we just did right here. Okay? So, we'll let you guys get going on that.